Okay. Just so you know where we're headed, we're going to end today at this point here. Oh, not that you saw, but sorry, but that point there. Some of this should look familiar because we did go through it in Algebra 1, so some of it will be a review. All right, any situation that has a percent growth or decay over a unit of time can be modeled by an exponential function. Okay, notice not just any sort of growth or decay, but a certain percentage of growth. There are several scenarios that affect your daily life and your future financial success that are actually exponential functions. Understanding them better and being able to recognize a situation that would be represented by an exponential function is a skill necessary in this unit. There's 3 different models that our situations are going to fit into. The first type is when you have a growth, an exponential growth going on. It's going to fit into the model y equals a times 1 plus r raised to the t. And I'm trying to decide if I want to define the variables. I will, right here. Okay. So y, this is the final amount, whatever you're looking at. A is our initial amount. R is our rate of growth or decay. The key here is you have to write as a decimal. And then T is time. And we're going to have one other variable that pops up into this, but those are the key ones here to identify what's in our model. Exponential decay is almost exactly the same, except instead of increasing by a certain rate, you're going to be decreasing by a certain rate. So it's 1 minus r in the parentheses instead of 1 plus r. And compound interest looks like this. Now, this only applies in cases where you're dealing with interest or with money, and only in cases where you're compounding that interest, which we'll get talking to about in a little bit. In this case, P is what we call our principal amount. It's the same thing as our initial amount, but they usually call it, if it's money, they call it your principal amount. A is your final amount. R is the same, T is the same. And then N is your number of compoundings. Okay, so let's get right into it. Example 1. Sydney wants to attend a university for their specialty program of underwater welding. However, she needs to sign up for financial aid today and does not know how much a semester costs. However, she does know that in 2005 it cost $15,400 to attend there, and the average rate of tuition increase has been 11.2% a year since then. How much will it cost Sydney to attend school there next year? Okay, first of all, you have to decide, well, it's a percentage increase or decrease, and so you know it's an exponential growth or an exponential decay, but we have to decide which one it is. And the key word there would be increase, so I know that it's going to fit this model. And even though it has to do with money, there's nothing in there that talks about compounding interest, so I'm not even going to worry about that one at this point. We want to see the final amount, so I'm going to be solving for y here, so I should have something to plug in for everything else. A is my initial amount, so $15,400. My rate is 11.2, but I have to write that as a decimal. So to write as a decimal, it's like you're dividing by 100 or moving the decimal place over. So we're going to add 0.112. And then to the t power. Now t, these are going to be years since 2005. So next year, or next school year, would be starting in 2012. So that's 7 years after 2005. So we're going to put a 7 there. 7 years The rest of it's just plugging it out in a calculator. So if you take a calculator and we insert 15,400 times 1 plus 0.112 to the 7th, you get that value, 32,378.31. So pretty much doubled in 7 years based on that rate of change. Okay, let's do another example. Okay, example 2. Jake is rolling in the dough. He wants to invest the money in a local bank, but doesn't know what his best option will be. He does some research and finds 2 viable options. One bank offers 5.2% compounded monthly. Another bank offers 4.5% interest compounded bi-monthly. He sits down and whips out his handy-dandy calculator to figure out which bank would give him the better investment option if he put in $25,250 for 10 years. Okay, we're going to split this right down the middle since we're comparing 2 different ones. But I did notice one thing as I was reading. I'm talking about interest, and I'm also talking about it compounding, which means I'm going to use that slightly larger equation for compounded interest. Okay, and then let's figure out what goes in for each one. Let's let this first option be this 5.2% interest. So my P is going to be the same for both, 25,250. My rate of change here, if I make it a decimal, is going to be 0.052. And the number of compoundings, if I compound monthly, it's all in terms of a year. So in a year, compounding monthly would be 12 times per year. So N is going to be 12. And then in my exponent, I have 12. And the length of time I'm looking at is 10 years. Okay. And then it's punching it out. Now with these, because there's so many numbers going on, you just have to be careful. So if you're going to punch it all out on one screen, I would do it like I'm going to do it right now. 25,250 times 1 plus, and then I'm going to put that that fraction in parentheses, and I'm going to raise that to 12 times 10. It is important that you put parentheses around the exponent like that, otherwise it's not going to compute correctly. You end up getting 42,423.51. Okay, so that's not too shabby. You've almost doubled it in 10 years. And 5.2% isn't a huge amount of interest, so that's good. Now let's do the same thing. 25,250. And now we have a different interest rate. So we have 0.045 over, now it says bi-monthly, so that's twice a month. So that's going to be 24 times. And we have 24 times 10 in the parentheses, in the exponent. We'll do the same thing. 25,250 times 1 plus 0.045 divided by 24 to the 24 times 10. You end up getting 39,583.20. Okay. Now, this one's going to be the better option if he only leaves it in for 10 years. But let's talk about what maybe compounding means here. Compounding basically means if you have, let's pick a better number. Let's say you pick 10%. Or even better, 12%. Okay? So if you have 12% interest and it's compounded monthly, that means the bank is taking this amount of interest that says, I'm going to give you 12% interest per year. And then I'm going to divide it by 12 so that every month you get 1% interest. And so at the end of the year, it's added up to that 12% interest. Why compounding is better is because in January, you have, let's say, $100. They add 1% interest, you get 101. The next month, you get another 1% interest, but now that 1% interest is on the original amount plus the interest they already gave you. So So it's like interest upon interest. And so the more you can get interest on interest, the more your money is going to build quickly. So even though this one ends up being more, it actually isn't that much of a difference, especially since you see such a big difference in the percentages. This one has a bigger growth, so we do assume it's bigger, but there's really not that much of a difference between the two when you look at it. Okay, basic rule of thumb, get the most compoundings you can because it's more interest on interest, and get a good interest rate. All right, let's look at example 3. Example 3, Andy just bought a new truck with all the trimmings for $54,000. His truck is magnificent, but sadly it's already worth less than when he bought it. Andy decides to upgrade 8 years later and try to sell the truck for $45,000. However, no one is coming to look at it, so he sits down to figure out if his selling price is reasonable. The average value of his truck decreased 16% per year. What would be a reasonable price for Andy's truck 8 years after he purchased it? Okay, now I see a percentage and I see the word decreased, so I know it's an exponential decay. So there's my model. Y is going to be the final amount of the car after a certain period of time. A is the original amount, which was $54,000. It's decreased 16%, so I'm going to subtract 0.16. And then we want it for 8 years. Okay, so 54,000 times 1 minus 0.16 to the 8th. You end up getting 13,385.30. Okay, so unfortunately, it decreased quite a lot. And that's why buying new vehicles is probably not a good money decision, just because you lose so much value straight off the bat. The best option to buy a vehicle money-wise is to look for a vehicle that's got good mileage, but is about 2 years old. And then you're still getting a pretty new car, but it's lost. You've avoided the huge hit of decreasing worth right off the bat, and then it's more what it really is worth. Okay. Let me see what time it is here. Okay, that'll be the end of this video. So actually, we've ended here, and we'll pick up with this on Friday.